In general, when we look at the popularity of a product, a service, there are two main factors involved. One is what we call an intrinsic value. Okay, this is, for example, when you enjoy certain music or buy a particular product just because you like it, whether the rest of the world agrees with you or not. In contrast, the second one is called the network effect. That's because what you do and decide depend on what others do and decide. And there could also be two possibilities of that. One is we've got information dependence, because the fact that others use something gives you some information. And this may lead to what we call information cascade coming up, or in other words, the fallacy of crowds instead of wisdom of crowds. The second type is because the fact that others use the same product gives you a higher value on this product. A typical example is the fax machine. When you're the only one with a fax machine in the world, then it's actually of no use to you. And the more people with fax machine, the higher the value of that product is to you. And similarly for Wikipedia, exhibiting a strong positive network effect through this valuation. So we're going to be looking at different models for information network effect, for valuation network effect, and coupling with the intrinsic value. For this lecture, we'll stay with population-based models, meaning that whatever happens in the model depends only on the number or the fraction of people adopting a certain product or service. There is no topology involved. And we'll be looking at two types. One is deterministic interaction, in the example of information cascade. And then in advanced material part of the video, synchronization models. We'll also be looking at random interaction models, including tipping, and later in advanced material also diffusion. Then in the next lecture we'll look at topology-based model, where the graph and the matrices associated with the graph come into the picture. For any of these models, there are at least three questions we want to formulate more precisely and then try to address. The first one is, what is the distribution of the nodes, whether you know the graph or not, in different states at equilibrium? So we have to define the states, and we'll see binary states, we'll see three-state models and many-state models. And this is a question about equilibrium behavior. This could be the Nash equilibrium through dynamic interactions of best responses, could be the equilibrium of convergence of iterative algorithms, and so on. The second question then is the amount of time it takes to reach an equilibrium. That means we have to define a time slot. We'll see that most of our models will assume a discrete time slot as usual in this course, but there are a couple of exceptions where we also assume continuous time, just to make the math in those models more tractable. The third question is often much challenging: transient behavior before reaching an equilibrium. Now, which model to use? That highly depends on what you want to do. Okay, are you trying to model that the fact sometimes people act at the same time? Then maybe synchronization model is what you want. Okay, or maybe a few early adopters changing other people's minds. Then maybe you want diffusion model or contagion model. You want to say a few people carry the whole system over some threshold. Then maybe a tipping model would be more appropriate. So each of the mathematical models we're going to be looking at is motivated by different practical use, and we will have to be careful as to which one to adopt. So here is a basic division of the models we'll be looking at. We'll look at population-based, where topology doesn't matter, before we move on to topology-based in the next lecture. We'll look at deterministic interaction among the nodes, as well as probabilistic random interaction models. We will look at info cascade, First, in advanced material, we'll look at synchronization. Then we'll look at tipping for a random interaction model, followed by diffusion in advanced material. So these two will be in the advanced material part. And for topology dependent next lecture, we'll look at contagion as well as infection, based on whether it's deterministic random interaction, and in advanced material also random walk, which we saw a little bit from Google's PageRank early on.